In this video, we're going to look at measuring the standard electrode potential of some slightly different half cells that don't have solid metal as part of the half equation, and therefore we might need to look at our electrodes more carefully. Okay, so we're going to start by doing iron-iron half cells, where both species in the half equation are aqueous ions. So we can see our examples. The first one, we've got tin 4 plus to tin 2 plus, iron 3 plus to iron 2 plus. We've got the dichromate to the chromium 3 and the manganate to the Mn2 plus. So remember, the half cell must include both the oxidized and the reduced species. So what we mean by that, we've got our oxidized species, our species here like SN4 plus, Fe3 plus, dichromate, manganate, and our reduced species, we have to put these in as well. Now, because there are no solid metals in our half equations, we're going to use a platinum electrode. Remember, in our platinum electrode allows electrons into the circuit. It's inert, so it doesn't react. So let's have a look at our first example, which is this equation here, the Fe3 plus Fe2 plus. So remember what I said in the previous video, you want to start with the species on the left, give yourself a little gap, draw a reversible arrow because we don't know which direction this would go in our cell anyway, all written as reductions, and then balance the equation with electrons. Remember, when measuring the standard electrode potential, we put the hydrogen half cell on the left hand side. So we've got the 2H plus 2 electrons goes to hydrogen half cell. So for that, the gas goes in through this little chimney at the standard pressure, 100 kilopascals. The platinum is used as an electrode because we haven't got a solid metal, and this is our 1 mole per decimeter cubed, something that is H plus, so I'm going to use HCl so I don't have to change the concentration. We've got our high resistance voltmeter. And we've got our salt bridge, which contains potassium nitrate. And then on our right hand side, we've got the two species. Now they're both AQ, so they both need to be in this part of the beaker where the solution is. So we need 1 mole per decimeter cubed, something that's Fe2 plus. So remember I've said before, we like nitrates. The good thing about nitrates is you just put as many nitrate ions as you had the charge. But we also need in this beaker 1 mole per decimeter cubed of the Fe3 plus as well. So we want iron 3 nitrate. Okay, so that has, i.e. Fe2 plus and Fe3 plus, both 1 mole per decimeter cubed. That's what we're aiming for. Squeeze that in. And because neither of those is a metal solid, they're solutions, we're going to use a platinum electrode. When the cell is set up, the voltmeter reads 0.77 volts, and the platinum electrode of the iron half cell is the positive terminal, which means that it's a plus value here. Remember, electrons always flow to the positive so that they can be gained. So this side must be the negative electrode. So the electrons are going to flow from the hydrogen half cell to the iron 3 plus, iron 2 plus half cell. When we do these slashes, it's always the highest oxidation state first. So written from left to right for a reduction reaction. How do we do the conventional representation? So remember, we start with the salt bridge in the middle. The right-hand beaker, highest oxidation first, so Fe3 plus AQ. Lowest oxidation second. These two are the same state symbol, so we're not going to put a phase boundary, we're just going to put a comma to separate them. But you cannot connect a crocodile clip to iron 2 solution, so we're using a platinum electrode, and a solid and an AQ are different state symbols, so we put a single line between those two. On the other side, we've got the hydrogen half cell, remembering that H plus is the higher oxidation state, so nearest the salt bridge. Hydrogen gas is the lower oxidation state. They do have a different state symbol, so they get a solid line. You can't connect the crocodile clip to the hydrogen gas, so you put the platinum electrode in, and that has a different state symbol as well. And we've finished our conventional representation. Remember that our electrons are going to flow towards the Fe through the external circuit. What about this one then? So this is the manganate. So up here we do actually have the half equation, but let's try to construct it as if we were in the exam. So the first thing that we've got to write is MnO4 minus AQ. Give ourselves a little bit of space, draw our reversible arrow, write the second thing, Mn2 plus AQ. And then to balance this half equation, remember we add water to balance the oxygens. Then we add hydrogen ions to balance the hydrogens in the water. And then we balance the charge with electrons, and we've got our overall half equation. Remember, we put the hydrogen one on the left-hand side, so we've got hydrogen gas at 100 kilopascals. We've got 1 mole per decimetre cubed, something that contains H+, so I'm going to go for HNO3 this time, and a platinum electrode. Got a high resistance voltmeter. So the left-hand side, when measuring the standard electrode potential, is always the same. It's always that hydrogen half cell. We're going to have a salt bridge containing KNO3. On our right-hand side, we need to have all the things in this half equation. Now, none of them are solid metal, so we're going to use platinum again. We need to put into this beaker everything that is needed for this half equation. So we need MnO4 minus at 1 mole per decimetre cubed. But MnO4 minus is an ion, so we need to put it with something. It's a negative ion, so let's put it with a positive ion, a metal. So maybe that, KMnO4. We need 1 mole per decimetre cubed of Mn2 plus. So Mn's a positive ion, so I'm going to put nitrates with it. That's also AQ. And we also need acid in this half equation, so I'm going to use 1 mole per decimetre cubed of an acid, so let's say HNO3. You could put half a mole of sulfuric acid in there or something like that, as long as we've got 1 mole per decimetre cubed. When you connect this up, the voltmeter reads 1.51, and the manganate is the positive, which means the electrons flow towards the manganate half cell, which means it's got a plus sign. So electrons flow from the hydrogen half cell to the manganate half cell. Conventional representation. We could do the left-hand side first here. We know that hydrogen ions are the higher oxidation state. Hydrogen gas is the lower. They've got different phases, and we've used platinum as the electrode. On the right-hand side now, watch out, don't fall into this trap. A minus isn't the oxidation state. The manganate is +7, and then it's +2. So MnO4 minus is the highest. And the MnO4 minus is acidified, so we're going to put H plus next. That's because that's in the half equation with the MnO4 minus. And then we're going to put the Mn2 plus. And they are all AQ, so they're just commas. And then we've got the platinum solid. Okay. So I think we've got one more example here. This is chlorine chloride. So Cl2, leave a gap. Chloride, AQ. So 2 chlorines, 2 chlorides, and we've got 2 electrons to balance the charge. So same again, left-hand side is hydrogen, 100 kilopascals H2 gas. A platinum electrode. something that contains 1 mole per decimetre cubed H+, so I'm going to use half a mole of sulfuric acid this time. Salt bridge, KNO3, high resistance voltmeter, and then on our right hand side we're putting our chlorine half cell, so we've got a gas here of 100 kilopascals chlorine gas. This will be our chloride ions. So 1 mole per decimetre cubed of Cl minus ions, so let's go KCl. Which would not be a good time to put KCl in your salt bridge because you'd be changing the concentration of the KCl in the right hand beaker if you did that. Platinum solid because we don't have a solid metal. The voltmeter reads 1.36 and it says that the chlorine's the positive, so it's positive 1.36. Electrons flow towards the chlorine. So they flow from the hydrogen to the chlorine half cell. So on the left we've got hydrogen ions and hydrogen gas. Hydrogen ions having a higher oxidation state. We're using a platinum electrode. On the right hand side, Cl2 is 0 and Cl minus is -1, so Cl2 gas first, that's a different state symbol to Cl minus, which is a different state symbol to the electrode platinum.